This is Free Range Digital Design Foundation Modeling, Chapter 8. This is the second video in Chapter 8. Last video we designed half and full adders. In this video what we're going to do is combine half and full adders in such a way as to create a ripple carry adder. So ripple carry adders, what we want here is a multi-bit adder. We have two different types of single bit adders. What we want is a multi-bit adder of any width we want to create, and what we want to do is be able to create that width very easily. And so ripple carry adder, simple concept. It's going to provide the functionality we're looking for. So this is significant because it's our first iterative modular design circuit. It'll be one of 3 IMD circuits. More significantly, it's our first foundation module. Keep in mind, we already mentioned it, ripple carry adder is going to be a bunch of full adders and half adders placed in such a way as to create an n-bit adder. This is a model for a 4-bit ripple carry adder. It's something that someone has to show you. You can't really design it from scratch. But the idea is this is your top level 4-bit ripple carry adder, meaning it's a 4-bit adder, meaning it adds 2 4-bit values, generates a 4-bit sum, should have been sum there, but it also has a carry out. The way we're going to create this is using a half adder in the LSB position. This is the MSB position, and all of these other positions other than the least significant bit are going to be full adders. The least significant bit can be a half adder in this case. So what we have here is a 1-bit adder. This is a 1-bit adder, but it may generate a carryout. This carryout is fed up into the carry-in of the next higher order bit. Now this is called a ripple carry adder because at any given time you're going to have all these input values there and ready to be added, but it's not going to necessarily be correct. The sum bits are not going to be correct until that ripple gets a chance to ripple through this thing. So if I'm adding 0 plus 0, that's of course going to be 0. There's going to be no rippling of a carry through all these individual 1-bit elements. The result's going to be available immediately. But if I add something like 1 plus 1 plus 1 plus 1, 0, 0, 0, this is an example where immediately this will be the answer. That's immediately just after the signal propagates to the half adder. But what's going to happen is that carry is going to come over to the next higher order bit, and it's going to change the output of this thing. So in the end, when I'm doing this math, by the time I'm done, this is 1 plus 1 generated 1, 1 plus 1 generated 1, 1 plus 1 generated 1, 1 plus 1 generated 1. Okay, so that's how the ripple carry adder works. It's very simple, not the fastest adder around, but it's simple and it's the one we pretty much always use in digital design. So if I needed a 20-bit adder, I just keep adding full adders to this thing. If I need a 64-bit adder, I keep adding full adders. So let's do a quick example here. Now, what I've done here is I've created this RCA with a carry-in. So what that means is I've inherently removed the half adder from the least significant bit position and replaced it with a full adder. And so now for this 4-bit ripple carry adder device I have sitting here, it's going to have a carry-in. Typically, for ripple carry adders, if I need a carry in, I put it there. If I don't need a carry in, I leave it out. This example happens to leave it in. So it's doing 4-bit math on this problem here. And so once again, I'm going to chop this up into sections so I don't make a mistake on this thing. To do the math on this thing as I'm trying to write these things out and talk anyway. So once again, 0x is the escape character for hex, meaning anything after that 0 hex is interpreted as a hexadecimal number. So here we go. So this 0x01 is actually 0001. So we've got, notice that the problem states that the C in here is always 0, which means we don't need to put it in the timing diagram. So the sum here, 1 plus 1, a plus 1 plus 1 is 2, so the answer is going to be 0x2, and there's no carry. Looking good. So next time the vertical line here, after this time slice here, the B input changes from 1 to F. I have F plus 1, which is 16, so the result's going to be 0x0, and that's going to generate a carry. Actually, it's a single bit, so I can represent it just a signal without the bus notation. So here I have F plus 0, which is going to be F. There's going to be no carry. 4 plus 6 is 10. 10 in hex is going to be A. No carry. A plus 6 is 16. That's greater than 4 bits, so this is going to be 0x0, and it's going to have a carry. 0, once again, the A plus 0 is going to be A, and no carry. 1 plus 8 is going to be 9, no carry. 4 plus 8 is 12, 12 in hex, 0xc, no carry. E plus 4, E is 14, 14 plus 4 is 18, so it certainly is going to have a carry. And wow, I'm having trouble doing that in my head. If in doubt, just write it out. 0, 1, 0, 0, there's the 4. There's the E, 0, 1, 0, 0, 1. So that's going to be 2. So this is my 2 right here that I'm going to put down here. Here we have B plus 6, which is 11 plus 6, which is 17. So that's going to be, I know what this one is, 0x1. You could do the math if you need to. It's also going to have a carry. 4 plus 9 is 13. That's less than 16, so it's not going to have a carry. So 13 is going to be 0xd. And lastly here we have B plus B. B plus B is 11 plus 11, which is 22. So that's going to be 0x6 with a carry, and I'm actually not super sure of that. 1, 0, 1, 1. So I'm going to add B plus B here. That's a 0, carry the 1, a 1, carry the 1, 1. And that looks good. I got it right. Okay, that's it, folks. Another example here, this a little bit more complicated example, is to take this 4-bit ripple carry adder and create a 8-bit ripple carry adder using 2 of these 4-bit ripple carry adders. Now, it wouldn't be too complicated to create an 8-bit ripple carry adder by simply taking a 4-bit ripple carry adder, adding 4 more half adders to it, but we want to do this in a modular format, and notice that we also want to state what controls this circuit, so we'll do that too. So the idea here is our final answer is going to look like this. Yeah, not super well planned out here. It's an 8-bit ripple carry adder, and there's our BBD for an 8-bit ripple carry adder. The key to this thing is realizing that to make an 8-bit adder, we need 2 4-bit adders. So I'm going to plop them down here. The trick on this thing is to wire it correctly, or connect the signals correctly. Out here, somewhere out here, I have an 8-bit signal coming in. Okay, so what's going to happen with this 8-bit signal is I'm going to divide it up between these two 4-bit inputs on the 4-bit ripple carry adder. It looks kind of cryptic, and so I'm going to put a note on this thing. So this is going to be A, 7 down to 4. And this is going to be A, 3 down to 0. So that's saying that The most significant bits are coming up to this top ripple carry adder, and the least significant bits are on the bottom. Okay, so looking good so far. So we're going to do the same thing with B. Starts off at 8 bits. I use my little fancy terminology here, which is a square with a minus in it to indicate that I've lost bits on this thing. This is going to be B7 down to 4, and this is going to be, oh, forgot it in there, B, this is also 4 bits. It's going to be B3 down to 0. Okay, so I've divided these things up equally. This bottom RCA has the 2 lower, least significant 4 lower bits of the original 8-bit A and B values. The upper ripple carry adder has the 4 most significant bits of the original A and B values. So we're almost done on this thing. What we have to do here is say this is going to be sum of 3 down to 0. It's also a 4-bit value, and this is going to be a 4-bit sum. This is going to be sum 7 down to 4. And what I'm going to do here is clump those together, make an 8-bit signal out of it. This is the 8-bit signal, which is the final sum. That looks pretty good. The only thing we have to worry about is the carry-in. And what's going to happen here is this bottom device is going to generate a carry-out possibly, and it is going to feed, not well planned out, up into this carry-in of the upper ripple carry adder, and appropriately here this bottom ripple carry adder is going to have a carry-in which I'm going to ground. And you haven't seen this before. This is my ground symbol, which indicates it's inputting a 0. Remember, these ripple carry adders are adding A plus B plus the carry-in. And so there's my fancy problem. This is a circuit without control. Ripple carry adder does not have a control. We'll see that in a second. But I've created a circuit with this thing, and I'm almost done here. This is the final carry-out. Wow, I picked the right major. So we mentioned before the ripple carry adder is our first foundation module, and this is our generic diagram for our controlled modules. A ripple carry adder is a controlled module, meaning it has data coming in, data coming out, typically control coming in and status coming out. Now if you relate that to the circuit we just generated, which is a ripple carry adder, here's our foundation module notation for ripple carry adder, an n-bit ripple carry adder for that matter. It has 2 n-bit inputs, which are the A and B operands, and an n-bit output. These are data. It also has a carry-in, which is also considered data. It also has a status output. The carry-out tells me something about the operation that ripple carry adder just did. It's a status output. Now the reason this circuit we designed a couple slides ago was considered to have no control is because this device here does not have any control input, so therefore it is a device that has no control, so no control on this. So notice that the carry out here is actually the nth plus 1 bit. So if this was a 10-bit ripple carry adder, this would actually be, the carry out would be considered the 11th bit if you want to do it that way. And there's oftentimes where that's something you want to do.